How's it going, guys? So this is a fluid mechanics problem, a Navier-Stokes equation problem. There's a viscous fluid, contained between two infinite horizontal parallel plates, spaced zero point 0.5 inches apart. The bottom plate is fixed, meaning it's not moving. Velocity 0. Upper plate moves with a constant velocity u, right? And later they give you that u to be 2 feet per second. The fluid motion is caused by the movement of the upper plate, and there is no pressure gradient in the direction of the flow. The flow's laminar. They give you dynamic viscosity 0.03 pounds seconds per feet squared, specific weight of 70 pounds per feet cubed. They want you to find the horizontal force per square foot on the upper plate to maintain that same velocity. And they also want you to find the pressure differential in the fluid between the top and bottom plate. So let's go ahead and get started. All right, guys, so I just started off with the givens, right? The bottom plate is fixed. They're spaced 0.5 inches apart. U1 is moving to the left, positive 2, right? So it's to the right, I'm sorry. So it's a positive 2 feet per second. They tell you that there's no pressure in the flow direction, which is the x direction, so that's 0. They give you dynamic viscosity, and then they also give you specific weight of the fluid. So they're telling us to find the force per feet squared, and then the change in pressure along the y direction. Okay, so these problems are very easy. Just follow this rule of thumb for every problem. Same steps. It's just different terms get canceled every single time. But you always start off with the Navier-Stokes equation, okay? So in this case, our coordinate system is xy. So I'm sticking to Cartesian. I am going to use the x component because that's the direction of the flow, right? So if I pull out my Navier-Stokes equations right here, I'm going to be using this one. Okay, that's what you see here is just a little modified. I like this version. This is the ones that the book typically gives you. But all I did was just divide by density. Look at all these terms on the left side of the equation. They're multiplied by density. I just divided everything by density. That way, this becomes into that, right? G of x, the density here goes away, right? It went away. And then the mu, because of this formula, becomes dynamic viscosity becomes kinematic viscosity, okay? So nothing really changes. That is the equation we use again, because that is the direction that the flow is going in, right? So we chose our coordinate system to follow the flow. So it's just xy. And the reason I say that is because some examples sometimes will tell you there's an inclined plate, and you might have to tilt this axis to follow that incline and to make your life easier. But in this case, it is, even if it's a tube, right? It's still, actually, no, I'm sorry, no, it wouldn't. But no, in this case, they're plates, so you're using xy. In a tube, you would use the radial direction, cylindrical coordinates. My bad, went too quick there. But yeah, you start off with the equation itself, right? So nothing here, right? I just got this from the book, and this is every problem. This is how you start them. Then you start canceling some stuff out. So let me show you what I'm doing here. Okay. It's steady state, right? All problems are steady state, especially if you're doing your undergraduate, your bachelor's degree. You very rarely you'll go into unsteady state. I mean, that's if the professor wants to be mean, I'm gonna be honest. If you're a graduate student, maybe. If you're a PhD student, yeah, most likely you're not gonna be dealing with steady state problems. But for most of you, you are gonna be dealing with steady state. So knowing that, this term goes to 0, okay? It's dependent on time, and it's steady, so that's 0, okay? The flow is in the x direction only. There's nothing in the y or into the paper, z, right? So that means v and w are 0. U is something, right? Because there is flow going in the x direction. This is x, y, z, okay? So that means v and w are 0. So because these two are 0, actually, I don't think I showed it here, but oh no, actually no, I'm sorry, I'm going too fast again. V and W are 0, okay? So these terms will get canceled out. So these two. So now, and then we know this one got canceled out because of this. So now we're left with this on the side, okay? Just keep that in mind. They told us that the pressure gradient in the x direction is 0, so that goes away. We'll go to the body forces soon, but hold on, just hold on to that one. Then we're gonna start looking at the other terms, right? In this case, infinite plates. So what this means is going into the paper, it's infinitely long, that the flow maintains its same shape kind of thing. And I drew this here so you can kind of see what I'm talking about, right? It's these two plates going into the paper, and I'm kind of assuming the flow like this, right? Because this is moving. Think of it logically, right? You guys are engineers. Move this plate, but keep this one still. The flow is going to be really high here, and then less, and then less, like a triangle, right? And that's what I'm assuming here. And look, going into the paper, it's the same thing no matter where you at. So that's kind of what this infinite plates assumption is saying, right? The change in U, which is the flow in the x direction, the velocity in the x direction, does not change with z. So it's the same here, it's the same here, here, all the way into the plates, right? So change of u over change in z is 0. So just take another derivative of 0, that's another 0, okay? That's all that happened there. So that's good, right? Because we canceled out this term, delta u over delta z. This one right here is the important one because we canceled this out right here, okay? I mean, that delta u over delta z also got canceled, but w was already canceled. So, I mean, we didn't really gain much there. So now we're going to go to the conservation of mass, okay? This fluid mechanics, you guys are going to be using this for the remainder of the class. I'm sure you guys have been using it already, but mass is conserved. So this is just the conservation of mass in the x, y, z and Cartesian coordinates. We know v is 0 and w 0, right? So that means take the partial with respect to y of 0. I mean, take the derivative with respect to anything, right? It's still 0. So delta v over delta y is 0, and delta w with respect to z is 0, right? Because this is 0 already. So take the derivative of 0 with respect to anything, you'll get 0. So that means this is 0, right? Because if these two are 0 and all this equals 0, then we know delta u over delta x, or partial u partial x, is equal to 0. Take the second derivative, again, it's 0. You see how these problems get real easy real quick, especially for you bachelors, guys. You guys are lucky. I wish I knew this, right? I didn't learn this in my bachelor's. I learned this in the master's. So this is the way I started doing them once I got to the master's. So delta u, delta x is right here, and that goes to 0. So cool, this was something, but because this is 0, this whole term is 0. So now this is 0, 0, 0, 0, 0, something. We got this to be 0, right, because of here. And then we got delta squared ux squared is 0. So now we're left with this one and kinematic viscosity and this one, okay? Now let's go to the next one, body forces, okay? Forget about this step for a second. We're on step 4, body forces. So the fluid is moving in the x direction, okay? There are no body forces in the x direction, but there are some in the y direction, and that's just the gravity of the fluid, okay? That's all it is. It's the gravity of the fluid is your body force in the y direction. But remember, we're doing x direction. So just keep that in mind, okay? So this is 0 in the x direction, and in the z direction, it's also 0. There are no body forces acting on your system that's causing you to that's helping you move your fluid, okay? It's just gravity in the y direction, the weight of the fluid itself. Now let's go to step 5. It's just the Navier-Stokes equations reduced. So in this case, these were the equations, remember? Let me move it like this. The equations were x, y, z for Navier-Stokes and Cartesian coordinates. So let me go ahead and run through this one real quick. Mainly, x is the one you got to focus on because you're focused on the velocity profile in the x direction and how it varies along the y. So does it do this? Does it do this? Does it do this? Whatever the case is, right? That's what this problem is kind of guiding you toward. In the x direction, we already kind of simplified it all. So as you can see, g of x was 0, so that went away too. So now we're just left with kinematic viscosity times this, and that's what I'm left here. Because all this canceled a lot of things out, remember? And then in the y direction, let's go ahead and do it. Well, we know v is 0, right? So look at the y direction. v0, 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 v is 0. So all these terms go away. v, all these terms go away. So now you're left with these two. There's a pressure gradient in the y direction. That's what the problem is asking you. It's asking you, how does pressure vary from top to bottom, right? So that's going to be something. And then we know gy is active, right? Because gy is a negative g. And that's what I got here. My Navier-Stokes equation for the y component reduced to this right here. Very simple. So I move this term to the other side and I integrate, okay, with respect to y. So I get pressure, right, because that's delta pressure over delta y is equal to negative rho g. That's just a specific gravity, right? So pressure is equal to that, right? I just added the y, I integrated it, plus a constant, a function of x, okay? So just keep that in mind. And then for the z component, do the same thing, right? W is 0, so W 0, 0, 0, 0. Let me move it more here just in case you couldn't see, but 0, 0, 0. So all these terms go away, all these terms go away. GZ is 0, right? So this term goes away, and then you're just left with this. So the pressure gradient in the z direction is just 0. And boom, that's it, okay? So just something to keep in mind. See, just like that, we messed with this crazy equation, and we reduced it down to these. This simple one, and these just to kind of show your work. We're gonna need this one for this part, but for now, let's just focus on this one, okay? Top one. So let me go here. Let me kind of cover this up just in case, just to not confuse you guys just yet. So general solution, right? Divide kinematic viscosity to both sides, so that goes away. Now you're left with this is equal to 0, which is here. Integrate it, you get that. Integrate it with respect to y, right? You get that. So remember, this is how does the velocity profile in the x direction, right? U. This is velocity profile in the y direction, velocity profile in the z direction. This is velocity profile in the x direction. How does it vary along the y direction? That's how you read these problems, okay? How does velocity in the x vary along up and down y, okay? So just keep something to keep in mind. I mean, sometimes you're writing these terms, you don't know what they mean, but it's all good, you know? You gotta start making sense of it. So integrate it twice and you get this, right? From 0 to c1, right, is just a constant, the integral. Then this becomes c1y plus c2, another constant. So boom, this is our general solution right here, okay? That's not the answer, that's just a general solution. This equation could solve a lot of problems. It's gonna solve our problems by applying boundary condition, our specific problem. So we need boundary conditions from our problem to solve this differential equation, this general solution, okay? This was different. This was the differential equation. So let's go ahead and apply boundary conditions, right? We're looking at the plate, top plate, bottom plate, and that's what I have here, top plate, bottom plate. At y equals 0, we know because of no slip condition that velocity is 0, and that's what I have here. The plate's staying still, right? So we know velocity is 0 because of no slip. And then at point number 1 up top, we just know the velocity is equal to the u1, right? The velocity was given here, u is equal to 2 feet per second. So you solve for your constants, right? In this case, I should have solved for this one first, but in the test, you won't know, right? So, I mean, it really is just like a guess. Which one do you want to call number 1 or 2? In this case, I called this one number 1 and this one number 2, boundary condition 1, boundary condition 2. And boundary condition 1, I put at y is equal to b, so when you're at this height, your velocity is just equal to u1, right, from here. So that was number 1. Now for number 2, at y equals 0, I said, hey, I have a plate and it's not moving, so my velocity is 0. So when I did this one, look, I used this equation. So I put u is equal to 0, so 0 is equal to, and then I put, for every y that you see, you got to plug in the 0. So c1 times 0 plus c2. So it just means c2 0, right? 0 is equal to 0 plus c2. Now that I have c2, I can find the first boundary condition in this case, right? Now for u, this one right here, I'm going to plug in u1, which is, and then for every y that I see, I'm going to plug in b. So u1 is equal to c1 times b plus c2, but c2 was determined to be 0. So I solve for my c1. c1 is just u1 over b. Now that I have both constants, I can plug them in here, and that's my particular solution, right? And that is what I did on this side. So now that I found my particular my function, right, I just plugged in my c1. This is c1, right, u1 over b, and this was just U of Y. This was my general solution, but then after applying the boundary condition, now I have my particular solution. And this is called the Coutte flow. I don't understand these foreign guys, right? Who knows? It doesn't matter. All that matters is that this flow is just simply for a plate that's moving while the bottom one's staying still. And this problem does describe, this scenario does describe a lot of real life problems, right? It could be like, I'm trying to think of something, like imagine you're painting a wall, right? You have I'm sure you guys have seen the paint or the roller, the one that you move with your hand, right? Well, the wall's fixed, and I mean, you're applying some, you're painting it. So the fluid has this velocity profile. You can't see it, obviously, because you're applying it, but that technically that is what it's following. I think that is one of the, if I remember correctly, I think that is what this problem can be describing. But there's so many real life problems that this could describe, just FYI. But yeah, in this case, we just have our general solution. And what that means is, look, it tells me, that means I got this part right. Remember this assumption? Look, because, and believe it or not, when I first did this problem, I did assume it. I didn't do it and then like, oh, I'm just going to put that diagram on there to make it seem like I'm smart. No, you know, it really is just that simple. Our slope in this case is U1 over B. So U over B, I should have put U1, but it's okay. It's linear. So we know U1 and we know B, right? 0.5 inches, and this U1 is 2. So we know our slope, and then for every Y, you should be able to get the velocity profile. So plug in Y is equal, well, this is all 0.5, right? So plug in 0.25, and you'll get your velocity magnitude at that location, right? And it should be that one right there, somewhere around there. But yeah, so now that you have that, we could go ahead and find our shear stresses, okay? So for shear stresses, this is also in the book, these equations, these equations. Shear stresses for Cartesian coordinates, right? These are your normal stresses, and these are your shearing stresses. In this case, we're looking, the problem had asked for, the problem had asked to find the force, and we know force is equal to pressure times area, right? So, or stress times area in this case. So we know Txy, we could find it using the equations right here. That's given as dynamic viscosity is equal to the partial U partial Y plus partial V partial X. Okay? And if you imagine like the flow's moving this way, well, the wall's shearing in the opposite direction, right? It's like sliding kind of thing, okay? So in this case, I use that equation. I know U, right? The flow in the X direction, the profile, velocity profile. V is 0, so this term goes away. So I just have mu times this. Well, I'm sorry, not this. The partial U partial Y. So I take the derivative of this function with respect to Y. And it's just U over B, right? U1 over B. So that's what I have here. So now that I have U1 over B, I got to multiply this times area to get me force, right? Well, they don't give us an area of the plates. They just say they're infinite plates, but they want it per unit length, per feet squared, right? So we know area is just feet squared. So that's why on area, I assumed 1 foot. Okay, just keep it simple. You don't have to do anything crazy. So in that case, I'm just going to plug in Txy, right, for force. Txy times area. I plug in mu. I just added an A in the middle right here. And that's 1 anyway, so I'm really just solving for Txy. B had to get converted. This was 0.5 inches. I had to convert it to feet. So when I plug in all my numbers, right, B is equal to 0.5 inches or 0.042 feet. Mu is equal to 0.03 pounds seconds feet squared. U is equal to 2 feet per second. Gamma, we don't need it yet, but we'll need it. And then area, right? I found my force. This is per unit length. So this should have been per feet squared. My bad, I forgot to write it down. It's okay, no big deal. But this is per feet squared, okay? Pounds per feet squared. And that's kind of what it's saying. Look, that's how much shear stress you're experiencing in this 1 by 1 area, okay? This plate could be 500 feet. It could be 6,000. Who knows? All I know is per unit feet area, you're experiencing that much, that many pounds, okay, of force. And I mean, and that's how much the plate has to experience in order to maintain the 2 feet per second, what the question was asking. And yeah, so now that you have that, You just find the pressure differential in the fluid from top plate to bottom plate, right? What the question was asking. And I kind of wrote here a little note for you guys. Since there is no fluid in the movement in the y direction, right? It's all in the x direction. We're only dealing with hydrostatic pressure variation. And yeah, the pressure, remember from this side, let me move this over here. Remember this? So there's no, the statement that I just added, there is no F1x. So in this case, it really is just gamma times height, okay? PG, rho gy. So that's what it is. Rho g times height, and it's gamma times b, 0.5 inches. Converted to feet, we know this is 62.4 pound per feet. Actually, why did I use 62.4? It should have been 70. Oh, snap. I just caught that right now. Just change that, okay? That should be a 70. For some reason, I went with water. But, I mean, you might get some slightly higher, lower results because of this. But, you know what? I don't even have my phone on me. So, I have two phones, the one recording and then my other one. But, just put this 70 times this, and that's your answer, okay? So, that's not your answer. That's wrong. But yeah, it really is that simple, right? Navier-Stokes, for some reason, a lot of people think is complicated, but it really isn't. It's it just takes time. Always start off with your big equation, start canceling your terms, and then you'll see that it all gets extremely easy. So yeah, hope that helped.